Now record.
Okay. And yes. Okay. Now, my name is Dan Jansen. I'm a professor of conservation biology at the University of Pennsylvania. But I first came to Costa Rica in first came to Costa Rica in 1963. I first visited the tropics in Mexico in 1953, collecting butterflies when I was 14 years old. And so I have been sort of embedded in the tropics and tropical entomology ever since. So my jobs have always been that of a sort of half-time work at a US university and basically the other half of the year free to do my ecology and biology and biodiversity stuff, as we would call it today, in the rest of the tropics of the world, but focused eventually on, in the 70s, on Costa Rica. Now, so I'm going along being an esoteric ivory tower ecologist in the tropical forest, Winnie at my side doing the same things for vertebrates more than for insects. And that started in 1978. And in 2003, I was really stuck because I was collecting large quantities of voucher specimens for my ecological research. And those things were being piled up in museums, the Smithsonian, the British Museum, the CNC in Canada, Costa Rica National Museum, Paris Museum. And basically they were being piled up behind the taxonomic impediment, to put it in one sentence, which boiled down to the classical process we've all used to morphologically identify species, and especially species that were snatched out of this or that circumstance in the tropics. And so you didn't have the others related, you didn't have the other information that went with them, going with them on a little paper tag on the pin underneath the insect in a museum. And the names they were getting were the names that all of us can put on things classically identified for hundreds of years. And right in then, we were invited, Winnie and I were invited to a meeting in Cold Spring Harbor called by this guy, Paul Hebert, from the University of Guelph in Canada, just south of, near Toronto. And he stood up in front of a bunch of hardcore whole genome genetic people and said, you know, I don't care about the whole genome. What I would like to do is explore this one little bit of DNA, which I think we can use to tell species apart. So he was basically arguing for what we call today DNA barcoding. And the room reacted very negatively. Basically, they did not want a new genome person, a new kid on the block, interfering with their efforts. In the psychological sense, interfering, in the fundraising sense. And so I stood up after 2 days of these fruitless arguments between Paul and the genome people and pulled my comb out of my back pocket, knowing nothing. I didn't understand anything about DNA, and said to Paul, what I want to see is in what costs my comb, its size, my personal back pocket. What I want to see in that is the ability to do what you're talking about doing in your laboratory. And he turned around and said, well, you've raised the bar. And I said, well, that's the only bar that counts. If we can't use this, if it all has to go across your desk, there's no point to this. And so this argument continued. The meeting produced nothing, no conclusions, no report, nothing. Everybody was very upset. And the next fall, this was in March, in the fall of 2003, they called another meeting of people who had not been quite so upset. And out of that came our saying to Paul, I want to see that this really works. So I had reared a very large number of butterflies and have so in Costa Rica. And so I know who they are by their ecology, not by their morphology. And so I sent him a box of, I think about 18 or 20 individual specimens, which nobody on the planet could tell apart. I could, because I'd rear them. I know their food plants. I know what the caterpillars look like. I know their biology. And I sent to him and I said, tell me how many species are in this box. And he gave me back an absolutely perfect answer based on their barcodes. Now, today, I know that those all happen to be things which are pretty easy to tell apart by their barcodes, but I didn't know that. And it only took him a week or 10 days in his lab to send that information back to me. Well, that said to me, oh, whoa, this is just a whole other opportunity. And so that changed all of our research, because all of a sudden we had another way, in addition to morphology, to identify things, either in the field or by actually taking a leg off and sending them up to Guelph in a lysis plate and all that sort of thing, or an Eppendorf tube, and getting the barcode and then comparing it with other things. So that's how we got started. So we're chugging along doing that, and we got lots of pushback from lots of taxonomists. And what we learned was the same human thing that everybody learns in this kind of circumstance, is that you don't preach at people. That's not how you get people to flip, to understand the usefulness for them of this. What we found was that if you take a really good taxonomist somewhere who really knows his family of insects very well, and he can do a whole lot by morphology with his Costa Rican specimens that we've already reared for him. We know who they are, we know who they are, not by a Latin name, but by an entity. And you give him those to do morphologically. And he does so willingly. He gets the specimens, and all's just fine. And then you show him the barcodes for those same 350 specimens, for those same 35 or 45 or 55 or 100 species. And he's just blown away. Whoa, I don't want to look at any more of these insects from you until they have been barcoded already. So that's how we ended up moving one person, two people, three people over to gradually finding the value of incorporating the barcode with their morphology and with our field data as well. Well, so we're going along, chugging away, doing this. And we've known Mike Sharkey from way back. I can't remember now when the first time we met Mike, but he was the guy in Kentucky, in Canada beforehand, and then Kentucky, who identified our agathidine parasitic wasps from the agathidine or in the Braconidae. And he did them morphologically for us. So I've been having him do them back in the way before barcoding for a long time, and accumulating their host records and including the names that go with them and all that sort of stuff. And he describes some for us as well. Well, so he kind of knew about what we were doing, but all of a sudden, out of nowhere, when he retired, he suddenly decided that, whoa, this is something I want to invest serious time in. And so suddenly, all of a sudden, we had a braconid nutcase who really knew braconids very well, but who was very willing to dive into the very large number of thousands of species of braconids that come out of rearing in the ACG forest in Costa Rica by both rearing and by Malaise traps, and take those on. So that's the raw material that we keep trying to provide to people. We don't build the gadgets. We don't do the barcoding. We just get the raw material with their collateral information, and we pass that on to someone like Mike. So what you're going to hear about today is sort of Mike's view of all of that. Okay, so that's my introduction for Mike Sharkey. And I just say we are extremely indebted to him for being willing to take on this thing, which has the potential of being very unpopular in the taxosphere, very, especially amongst the older, more established pieces of the taxosphere. So that's my introduction.
Everyone, and thanks to Dan for that introduction, and to Neil for pushing me to put this presentation together. As a way of introducing myself, I've had a 40-year career working on the taxonomy of braconid wasps and describing hundreds of species in the process. I started using a morphology-only approach, and this was followed by a few decades of incorporating molecular data in what is termed integrative taxonomy. Most recently, I have co-authored 2 papers using a CO1 barcode approach, which largely ignores morphology. And the purpose of this talk is to demonstrate that the old way of doing things of describing Ichneumonoidea are problematic and must change if we are to deal with the great diversity in Ichneumonoidea. I am sure that many of these problems are shared by researchers in other species-rich data, taxa rather, but members of the audience can judge that for themselves. So there are two parts to this presentation. I will begin by giving you an idea of how many species of Ichneumonoidea exist. I then describe how our current approaches to describing species in this taxon fail. In a future presentation, I will discuss two alternative approaches using CO1 barcodes that may offer some improvement. Currently, we have two common approaches. One is morphology only, indicated by the highlighted letter M in this slide, and the other is what is termed the integrative approach, which employs both sequence data and morphology, indicated by the highlighted letter I. Some of the problems that I outline are shared by both integrative and morphological approaches, and others are restricted to morphology. In reality, all of the problems stem from the inclusion of too much morphological data. These problems are that the rate of description is too slow, it costs too much, the quality of the species delimitations are very bad, the keys don't work and never will, and the type there's an overdependence on type specimens. So I'm going to begin the talk by giving you all an idea of the magnitude of the task, how many species of Ichneumonoidea are. And what you're seeing here in this slide is the catch from a Malays trap that was set in my backyard in Arizona when I was on sabbatical there some years ago. You were like looking at a white pan trap that's about 12 inches wide, and the black mass consists of thousands of insects. I want to give you an idea of how many specimens and species of Ichneumonoidea and Hymenoptera are in the sample. In the next slide, I'm going to focus on that little green square. Note that it is an area with relatively low insect density. And there we have it. This small area has 14 specimens of Hymenoptera representing 14 different species, all of which are less than 3 millimeters long. These are indicated by the yellow dots. I know you can't see them well. Extrapolating from what I know about the Proconidae in the area, most, if not all, of these species are undescribed. And reviewing that previous slide, it allows you to realize the fact that there are probably hundreds of Hymenopterans in that 1 week Malays trap sample from one small spot in the world, and 100 or more undescribed species. We're not dealing with birds or butterflies here. Hymenopterans in general, and Ichneumonoidea in particular, are enormous groups. Well, how many species of Ichneumonoidea are there? Because our colleague Dickie Yu worked for decades on Taxopad, a catalog of the superfamily, we have an estimate from 2016 when he retired from his self-imposed job. 44,385 species were described at that time, so a little over 45,000 are described today. Of course, that doesn't tell us how many species there are. This is just the estimated number of described species at the time. These next few slides are a little bit tedious, but they are important to set the stage for the remainder of the presentation. I will extrapolate from taxonomic research that has been conducted on the subfamily Microgastrinae, which is one of the more species-rich subfamilies of Proconidae. Presently, Dan Jansen, Winnie Holwicks, and their team have reared approximately 1,000 species of Microgastrine from the caterpillars in the Area de Conservación de Guanacaste. From now on, I'll call it the ACG. That's that small green area in the northwestern corner of Costa Rica. They do not rear caterpillars from many sources, including those from the forest canopy, stem borers, leaf miners, and several other niches. And they are continually finding new species in the rearings that they do conduct. So the bottom line here is they have reared 1,000 species of microgastrines. Over the past few years, Dan and Winnie and their team have started to malaise trap specimens. They have now trapped about 660 species of microgastrines, only 30.3% of which match the reared species, indicating that approximately 30% of the species of microgastrines have been reared. Of course, this assumes that the malaise trap specimens are a random sample of all microgastrines. Extrapolating from this, there are approximately 3,300 species of microgastrine in the ACG, which represents only 2% of the land mass of Costa Rica. Having worked in the ACG for many decades, Dan and Winnie have extrapolated taxonomic groups that are well surveyed in Costa Rica and concluded that the ACG has about 65% of the species of all of Costa Rica. This seems like a high percentage, but the ACG is geographically diverse with Pacific dry forest, cloud forest, and Atlantic rainforest. This gives us an estimate of 5,077 species of microgastrine for the entire country. In Taxopad, Dickey's Ichneumonoidea catalog, the members of microgastrinae make up 11% of all braconiid species. If microgastrines constitute 11% of braconids, then there are 46,153 species of braconidae in Costa Rica. Interestingly, several decades ago, I was among a group of hymenopterists who were invited by Dan Jansen to begin an all-taxa biological survey of Costa Rica's insect fauna. At the time, I estimated 4,000 species for all braconidae, very far off the mark. Extrapolating again from well-studied groups, Costa Rica is known to have about 4% of the world's terrestrial species. For example, 4% of the birds, butterflies, and similar well-studied groups. This allows us to predict that there are a little over 1 million species of braconidae in the world. It is widely believed, and with substantial evidence, that ichneumonids have about as many species as braconids. For example, there are about 25,000 described species of Ichneumonoidea, and only 20,000 described species, there are 25,000 species described in the Ichneumonoidea, and only 20,000 described in the braconids. The estimated number of species of Ichneumonoidea then is a staggering 2 million species. This is not so strange when you understand that there are an estimated 1.8 million species of gallflies, Cecidiomyidae. So the one variable that I think may be inaccurate in this figure from the Ichneumonoidea catalog is that it places the microgastrinae at only 11% of the braconidae. So to correct that, I took a look at the relative composition of braconid families in Canada on BOLD, which is the most densely sampled country on BOLD. That's the Barcode of Life database in Guelph, Ontario. In Canada, 539 of the estimated 3,289 species of braconidae are microgastrines. That comes out at 16.4%. Now, Dr. Jose Fernandez, a microgastrine expert, resides in Ottawa and has been submitting many of this subfamily to BOLD. So this percentage is probably biased towards too many microgastrinae, making it a very conservative estimate. If we use the 16.4% figure instead of the Taxopad catalog figure of 11%, the total estimate for world species of braconidae is 773,933, and double that, or about 1.5 million species of Ichneumonoidea. But to avoid being accused of exaggeration, for the rest of this talk, I'll refer to the estimated number of world Ichneumonoidea at an even 1 million species. So the rest of the talk then talks about the problems that I see with our standard approaches, that is morphology only and integrative taxonomy. Of course, the most obvious problem is that we're going far too slow. So So again, extrapolating from the Ichneumonoid catalog, over the last 260 years, we have described about 45,000 species of the estimated 1 million species of Ichneumonoidea, representing a paltry 5% of the fauna. About 50% of these species are from the Palearctic region, which has been relatively well studied. So the remainder of the world, which has many more species, has had less than 2% of its species described. For example, the neotropical country with the most species in the catalog is Costa Rica, with 1,818 species. That's 2% of the estimated number for that country. Even if you add the approximately 700 species described by myself and Jose Fernandez over the last few years since the catalog stopped, it's still just 3%. Remember that Costa Rica is the best studied country in the neotropics, and it is not nearly the most diverse, with countries like Brazil, Colombia, Venezuela, Peru, and many others far ahead of it in species diversity. All other neotropical countries have less than 1% of their Ichneumonoid fauna described. In other words, 260 years of taxonomy have accomplished next to nothing when dealing with exotic Ichneumonoidea. This graph illustrates the rate at which species of Ichneumonoids have been described in the 260 plus years since Linnaeus. The positive aspect is that there has been a general increase over time. Since the year 2000, our community has been describing an average of 468 species of Ichneumonoidea per year. The bad news is that at this rate, it would take 2,041 more years to complete the inventory of the world's Ichneumonoidea. That's using the conservative 1 million estimate. This is what it looks like graphically. What we have accomplished to date in the Ichneumonoidea is that small blue blur in the left-hand lower corner. But remember, we have described the easy ones so far, the species with large specimens like those of the genus Megarissa, and those that are close to the world's major museums. What are left are the difficult, species-rich exotic taxa. And as all experienced taxonomists understand, the more we work on them using morphological diagnoses, the more time-consuming they are to treat, with more types to borrow, more museums to visit, more publications to read, more specimens to revise, and longer keys to add to. And there is some urgency. As the entire audience, I'm sure, knows, there is a crisis in biodiversity. The numbers of specimens are declining at a rapid pace, and it is certain that many are going extinct. I've been focusing my recent research on specimens from the ACG in Costa Rica, and will present over the next few slides some indications of the devastation that is taking place there due to global warming. This slide and a few others that follow are from an article Dan and Winnie published in the Proceedings of the National Academy of Sciences entitled, "To Us Insectometers, it is clear that insect decline in our Costa Rican tropics is real, so let's be kind to the survivors." In this slide, you're looking at a light sheet at the beginning of the rainy season in the ACG in 2007. And this is what it has looked like for decades. Thousands of leps and other insects crowd the sheet. This is what it looks like today, at the same time of the year, also with a dark moon. And clearly the biomass is greatly decreased. This same phenomenon of insect biomass loss has been documented in many parts of the world with various taxa and data. In Costa Rica, there are various explanations for this phenomenon. One that Dan and Winnie cite is that the beginning of the rainy season used to be very abrupt and predictable. Now the rainy season begins in an erratic fashion. Today, those caterpillars that hatch with the first rains often encounter long dry spells that greatly reduce their chance of survival. One of the most notable manifestations of global warming in Costa Rica is the decrease in cloud cover. As temperatures increase, clouds are pushed higher and higher to the point that they no longer provide the moist environment required by cloud forest insects. With the warming and drying of the Costa Rican cloud forests, army ants have colonized it with unknown but likely devastating effects on ground-dwelling species of arthropods and also vertebrates. They were once not seen above 1,000 meters, and now army ants range to 1,500 meters. For a more data-based demonstration of insect decline in Costa Rica, we can use the rate of caterpillar capture by parataxonomists in the ACG. Since 2005, there have been 25 parataxonomists steadily employed to collect insects, caterpillars or gusanos. From 2005 until the present, there has been a steady decline in the number of caterpillars that they capture, such that with the same effort, they now collect less than half the number of caterpillars that they did in 2005. More alarming to me is the decline in parasitoids. There are many fewer caterpillars, but on top of that, the percent of parasitized caterpillars is now 5%, down from an average of 10%. As caterpillars continue to become more difficult to find, it is the parasitoids that are more likely to go extinct, with unknown ramifications on food webs and ecosystem stability. We must speed up our rate of species discovery before many of them are gone. We need some areas of the world, such as Costa Rica, to have their arthropod faunas exhaustively documented now, so that we have a benchmark that we can use for conservation purposes. So we can talk about conservation in an informed and intelligent manner. So the next problem that I'll be dealing with is that the costs of our current approaches are far too high. Using the conservative 1 million species of Ichneumonoidea as a world estimate, the number of perconids in Costa Rica is about 30,000. What would it cost to describe these 30,000 perconids using current approaches? Max Fisher, who recently died, was the most productive modern perconid taxonomist, with about 2,000 species to his credit. Over the most productive 40 years of his long career, he averaged about 50 species per year, mostly in the subfamily Ophiinae, and he employed a strictly morphological approach. Again, I will be conservative and suggest that somebody could be a lot better than Max and could describe 100 species per year using standard morphology or integrative approach. Assuming that his salary, his technical help, overhead, publication costs, etc., it would cost, assuming these are about $200,000 per year, it would cost $94.4 million for people of his ability to describe all species of Costa Rican perconids. To describe the world's ichneumoniid fauna, it would cost more than $2 billion. And that's not the kind of money most granting institutions have. Okay, we've looked at the slow pace of standard taxonomy. We will now look at how accurate it is. The screenshot here that you saw earlier is from Taxipad, showing the total number of valid species of Ichneumonoidea. And beside it is the number of synonyms. So far, for every 4 species that we have described, 3 are valid and 1 is a synonym. In other words, the error rate is 33%, not very accurate. And synonymy is not the greatest error in taxonomic research in Ichneumonoidea. Much more common is lumping species. We need not look at wasps to demonstrate this. You are all probably aware that there are 4 or more species of giraffes, not 1, 3 species of elephants, not 2. Orcas are another example. And these are not the result of discovering new specimens that belong in different species, but rather variation was known, but the species were lumped together based on morphology. If we were to add the number of lumped species concepts to the number of synonym mistakes, many more than half of our species concepts in Ichneumonoidea are wrong. So we've described, what, 3% of the world's fauna, and more than 50% of those are wrong. We definitely have to change our approach. The only saving grace is that many species are described from a single specimen. Unfortunately, as we add specimens to our species concepts over time, it will only make the matter worse. In this slide, I show a real example of lumping. It's an error that I made in a publication with a student of mine on a group of Perconids from Costa Rica. These images show 4 cryptic species of Alabagris, a genus whose members attack caterpillars. We lumped all of these under the name Alabagris pachamama. I know we were wrong because we now have sequence and host data that clearly distinguish species limits for Costa Rican members of Alabagris. The holotype in Peru is the 5th species of Alabagris pachamama in this complex. This was not the sole error in the publication. We lumped species of Alabagris at the rate of 56%. But wait, it gets somewhat worse. This is from the treatment of the original description of Alabagris pachamama, the holotype locality indicated by the rounds, the bright red spot in Peru. Based on the 4 species in Costa Rica that we thought were pachamama, there are probably another 4 or 5 more species here in South America, and many more that would key out to Alabagris pachamama that we have not yet encountered. Here's another example. As a training tool for a new graduate student of mine, I had a competition with him. Ilgu Kang and myself tested our ability to morphologically differentiate the 32 species of Costa Rican little pilots, another Perconid genus. We had extensive molecular and host data for all species, but ignored these data for the test. After we incorporated the molecular and host data to establish the species limits, we discovered that we had error rates of 64% and 57% respectively. All possible types of errors removed: lumping, splitting, and both lumping and splitting. That is, mixing some members of more than one species into 2 or more incorrect species. A total mess. We saw earlier that the synonymy rate was 33% in the Ichneumonoidea. If we were to add the number of lump species concepts to the number of synonym mistakes, more than half our species concepts would be wrong, perhaps many more. The next problem I'm going to talk about are keys in these very species-rich groups of Ichneumonoidea. Even if species concepts were correct, keys do not work for these groups. There are very few revisions of hyperdiverse genera of ichneumonids. And over the next 2 slides, we will investigate 2 of these. Both are large revisions of neotropical ichneumonids. The first of these is my PhD thesis that was published in 1988. In it, 104 species of Alabagris were treated, most of them new to science. According to Google Scholar, the publication has been cited just 32 times. And given the amount of effort and time that publication cost me, I was rather disappointed to discover that. But the only one of these publications that has someone besides myself use the key to publish an identification, in only one of these publications has someone besides myself used the key to publish identifications of neotropical species. We know that I can't identify species of Alabagris based on my own key, as per the Alabagris pachamama example. And of course, other users should be just as confused. This slide is from a 2005 publication, which listed the species of Alabagris discovered in Brazil. They were identified using my 1988 publication. The holotypes of the species indicated in red are from Central America or Mexico, and the holotype of Alabagris marginatifrons is indicated in blue. It's from the eastern United States. The probability that any of these species occurs in Brazil is extremely low. Yet I am sure the Brazilian specimens get out just fine. When you have a key for about 100 species and a reality of more than 1,000 species, Almost any specimen will key somewhere. And we must ask, what's the damage being done by keys such as that? Presently, I'm revising the species of Mesochorus, an ichneumoniid hyperparasitoid, and it attacks mostly braconids, ichneumonids, and tachinids. The Janssen team has provided me with approximately 150 species of this genus. With similar extrapolations as presented earlier, this places the estimate number of species for Costa Rica at 324 and 8,100 species in the genus worldwide. My conservative guess is that there are about 3,000 species in the Americas. In perhaps the largest revision of any neotropical genus of Ichneumonoidea, Clement Dash described 245 neotropical species, representing 8% of the New World fauna. Dash included 15 species as occurring in Costa Rica, a mere 5% of the estimated fauna. His key is 279 couplets long and exceedingly difficult to run. If all 3,000 New World species were included in the key, it would be 3,416 couplets long. As with my revision of Alabagris, there are only about 30 some odd citations for Dash's 1974 revision, and only about 3 that attempt to identify a specimen using this key. Few people use these keys, and for good reason. The odds of these identifications being correct is almost nil, as I'll try to demonstrate in the next slide. Let's investigate what someone would have to do to identify a species using Dash's key. Above here on this slide is a normal couplet selected at random from Clement's publication. The problems that I see are, how do you measure the tempo and at what angle and height? It requires definition and tedious measurement. How does one measure the width of the areola, inner or outer diameter? Again, a time-consuming measurement is required, even if you knew which of those two to select. What is a large spherical versus a small spherical? Now imagine going through 20 or 30 couplets like this in the hopes of arriving at an identification for a Costa Rican specimen, especially when you know that the odds of it even being in Costa Rica are only about 5%. After finishing with the key, a large and complex description would be read with similar difficulties. If all 3,000 species in the New World were treated like this at some point in the future, even if the species concepts were correct, it would be even more likely to fail due to the probability of the key being erroneous or the user making an error in any point of the 1 or 200 couplets that he would have to go through, or he or she would have to go through. Morphological keys will never be the solution to groups like this, even if technologies like Delta or Lucid are used. As mentioned previously, there are few ichneumologists other than Dash and myself who have foolishly attempted to treat entire neotropical faunas for their very diverse genera. The vast majority of species-rich ichneumoniid genera are described a few species at a time in multiple publications. Take, for example, the braconid genus Aliotes, members of which are endoparasitoids of caterpillars. There are more than 1,000 species of Aliotes in the tropics, likely many more than 1,000 species, and 70 of these have been described in 24 publications. If we continue like this and describe all neotropical Aliotes in the same manner, it would take a minimum of 342 publications. In these cases, the ability to identify a species is even more difficult, and the taxonomic impediment is more extreme. Now, the last problem that I'm going to talk about is the overdependence on type specimens. This is an image of the KW Nipe building in Ottawa, which houses the Canadian National Collection of Insects. Because morphological keys and descriptions are inadequate, revisers must borrow the type specimens at significant cost and effort and time to both the identifier and the institutions housing the specimens. But of course, this is only for the privileged few who work in Europe, Canada, the USA, and a few other developed countries. Researchers from many countries get a polite refusal when trying to borrow specimens, citing customs problems and safety concerns, which are real. Although it is not meant to be, this has the effect of making taxonomy elitist. For those researchers who can obtain holotypes, there will be many encryptic species complexes, such as the Alobagrus pachamama complex that we looked at earlier. And these will, looking at the specimen, will not allow for identification any better than the key would. This is an image of the British Museum of Natural History. In order to revise neotropical species of Agathidinae, I had to visit all of the important European and North American museums. Let's look at the genus Zelomorpha as an example. There were 51 species of Zelomorpha described from the Americas when Sarah Mayrato and I set out to revise the Costa Rican species. But I had no idea how many there were until I visited all the museums housing. Species were described under 12 different generic names and housed in 11 different museums. Most of the descriptions were from the late 19th and early 20th centuries and were so brief that they were all but useless, even to determine the genus. Only after 6 weeks of touring European museums, as well as visits to the Smithsonian, the American Museum of Natural History, and the Philadelphia Academy of Science, did I find all the holotypes. It is almost like the original author discovers species, and the revisers, Sarah and I in this case, rediscover species in museums at even greater cost and effort than took the original person who discovered the species. I'm not suggesting that holotypes are not necessary. However, if holotypes were barcoded with sequence data, many fewer would have to be viewed in museums or borrowed. There are also social and environmental issues to consider. The cost of traveling to museums to view types is expensive, all but precluding the participation of taxonomists from developing countries. There was a cost to the environment and the air travel involved. And finally, in the case of pandemics, such as the coronavirus that we're experiencing, virtually no one can visit museums and our science is put on hold. To summarize, morphology-only approaches to the description of megadiverse taxa have 5 major problems. And most of these are shared by integrative approaches that combine morphology with their molecular data. But it's only because of the morphological component that these have a problem. They're too slow, they're too expensive, they're inaccurate, the keys don't work and never will work, and there is an unnecessary overdependence on type specimens. As a final reminder, the criticisms that I have just outlined, again, are only in reference to very diverse taxa. It's not for typical ones. For the next webinar, I will outline 2 quite different approaches, both of which are based on CO1 barcodes. And these approaches, I believe, have the potential to greatly reduce the taxonomic impediment. But I will say that these approaches are in their infancy, and they are replete with their own problems that have to be worked out before they can be implemented on a large scale. And with that, I'm through. Thank you.
Thanks, Mike. Okay, are there any questions?
Hey, Sonia. Oh, I can't say really. Too much anxiety, I guess. And I just got through listening to Sharkey describe his.
I'm sorry, could you repeat that? Did you say that you were still in shock?
I think the microphone was on inadvertently.
Oh.
So I have a question. How are we at the generic level as opposed to the species level?
It's quite problematic as well, and getting, in my estimation, worse. I don't think that the community of ichneumonologists is very interested in presenting keys to genera, for example. I'm now trying to put together the New World Manual for the Braconidae, all the genera of Braconidae for the New World. And it's very difficult to get collaborators. Bob Wharton, for example, retired some 5 or 6 years ago, maybe more. He took care of groups like the Alyssines and the Opieines. And now to get somebody to take care of the genera in those groups is very difficult. We're refining them slowly, but it's still, I'm not sure it's getting much better. That's my view.
So, Mike, it is theoretically possible to obtain physical specimens of every species and link that up with genetic data, but that literally could be 2 centuries from now.
Yeah, absolutely. Yeah, in the Braconidae, there are dozens and dozens and dozens of new genera in the Americas that are still not described. It seems quite endless to me.
Mm-hmm. And so you say that this is really directed at hyper diverse groups, but I guess I clearly see a need to integrate CO1 barcoding literally with every taxa.
Yeah, I agree that but I think that in the less diverse groups, an integrative approach is probably more applicable. I'm doing revisions now of the New World species of Ichneumonoidea and Eorinus. One has 4 species, the other has about 30 species. And for those, I think it's worthwhile to write a key and short descriptions. But when you get into genera that, when you get into genera that are really enormous, the keys are superfluous or worse. Mm-hmm.
Mm-hmm.
Yeah, and somebody made the point that CO1 doesn't work for all taxa, and that's certainly true too. And in the end, CO1 will certainly not be enough. I mean, this is a new ball game, and I can't imagine that in about a decade, we won't be using a suite of different genes instead of just CO1. It's a good starting point for most groups, and in the Braconids, it really works well. But yeah, it doesn't work for everything.
Okay, so if there are no other questions, we are at the hour mark. And so, but Mike, when do you expect to be able to give the second part of your webinar?
Well, I'm hoping to get it done before I go on vacation, which is June 18th. So maybe June 17th. If that's not a weekend, I'm not sure.
Okay. Okay, with that, unless there's no other questions, I will stop the recording and end the meeting, and thank everybody for attending and being patient with the technological problems.